We'll now go through some examples where we have applied quasars XPS to analyze nanoparticles. First thing to note when you are studying nanoparticles with inelastic background analysis is that you should not use a multi-layer of nanoparticles, because you will be seeing the structure of the whole thing here and not the individual nanoparticles. You'll get signal from the underlying nanoparticles. So you should make sure that you deposit a sub-monolayer of the nanoparticles on a substrate. Here's an example where we deposited gold on polystyrene. These are the spectra that were involved in the analysis. So just deposited increasing amounts of nominal thicknesses of gold on the substrate and recorded the gold spectra, gold 4F spectra. And here's the analysis of one example after depositing 8 angstroms. Comes out to be 36 angstroms tall. The analysis is quite good here. And we can see the uncertainty on the analysis. We can clearly discriminate between these two thicknesses, and the uncertainty on this thickness is about 5 angstroms. Now, if we include a reference spectrum from a gold foil, first analyze that in the usual way, we have the reference spectrum here to compare to. And it's clear that this gives a very good fit out here, but not in the peak. And that's because the concentration is much smaller, and this corresponds to an island. So when we change to island structure here, we get a very good agreement with the reference spectrum with 36 angstroms tall islands and a coverage of 23%. And now, because we have the reference spectrum to compare to, the uncertainty on the thickness is even smaller than the 5 angstroms we found before. And you might note then that if we multiply the 36 angstroms with the 23 coverage, we get a total amount of gold at 8.3 angstroms, which is very close to the nominal thickness. So this is what we have. And what we determine from the analysis is the height and the coverage of the islands. But now if we interpret these heights and coverages in terms of nanoparticles, then it's very easy to transform these numbers, the height and the coverage, into nanoparticle diameter and density. So we get indirect image of the nanoparticles in this way. And this is what we found for the different deposited amounts of gold, the nano cluster size in angstroms, and the density. For one of these, this deposit here of 3 angstroms, there was also taken a TEM image, which is shown here. And there's a very good agreement. As you can see here, we have the scale 20 nanometers, and we find a nanoparticle size of 3 nanometers, which is very close to what we have here in the image. And the density also is very close to what we have here. So now TEM is very time consuming, whereas the analysis of the XPS is much faster and much cheaper than the TEM analysis. And another advantage of the XPS analysis is that it's non-destructive, so we can sort of, just by keep recording the spectrum, we can see what happens as a function of time and temperature as the structure is annealed. And here's an example where the intensity of the peak is seen to decrease as the temperature is increased, and at the same time we have an increased intensity in the background. And the analysis of this is shown here. Before annealing, we have the nanoparticles on top, and this structure doesn't account for the spectrum after annealing. We need to have the nanoparticle embedded in the polystyrene. And it's easy to follow this as a function of time and temperature as the sample is increased, as a sample is annealed. Here's the result for one of them, and here's the result for a larger nanoparticle. All published in this reference. Coated nanoparticles is another interesting application. So we first look at a core shell platinum coated with carbon, and here's the XPS. What you see is we have a platinum, a peak here that we can use for analysis. Carbon is a little bit difficult because we have an overlap with this. It's possible to do it, but it's more complex. It can be done with the process generate software. The platinum 4D could not be used. Platinum 4P can be used. I'll share that in a little while. But we, of course, the most obvious peak to choose here is platinum 4F. And here's the analysis, and we get a rough structure of the nanoparticle here. Platinum from about 16 angstroms to about 95 angstroms. But now it's interesting to see if we could not use this, if there was another overlapping peak here, then you would start to look at the platinum 4P, because there's no interference with anything here. So now, show in the next slide, I take the platinum 4P and analyze that. And I get reasonable numbers here, not that far from the platinum 4F. Of course, the uncertainty is a little bit larger on the analysis of this smaller peak and more noisy peak. You see, I have also smoothed it a little bit. But you could record this with the better statistics if you wanted to. There's another example where we again have the platinum 4F, and here the nanoparticles are on Teflon, therefore we have a fluorine peak. From the platinum 4F peak, we get roughly the structure again of the nanoparticle. If we now take the fluorine 1S here to see how much information we can get out of that, we can again smooth the spectrum a little bit and analyze the fluorine 1S. It's very small, but you do get reasonable information out of it. So you see the correspondence here, the thicknesses here for determined from the fluorine and the platinum are similar. So what I want to show with this analysis is that even if you have very, very small peaks, you should still try to analyze them. You can usually get a lot of useful information. A low intensity is less of a problem than the problems you have if you have interfering peaks. You should really worry about that. And here's the final example. This is a recent example we did in a collaboration with Wolfgang Ungar and his group at BAM in Berlin. And Jan Müller was the primary author on this work. So what we started here was PTFE core and a coating of either PMMA or polystyrene. Different shell thicknesses were studied, and it's such that the PTFE, the core here, was 45 nanometers, and that's much larger than the IMFP, and therefore we can ignore the signal from these depths here, and the model to use, and we could use this model here for the PTFE signal. So we look at the fluorine signal, and for that we can use this structure here. And of course you will have different orientations of the nanoparticles, which you can discriminate then if you don't have an ideal coating where the coating thickness is constant in all directions. So here's the analysis of the PMA coating, and you see we get for a 5 nanometer thickness, we get a good account for the background here. This is the fluorine 1s and the fluorine Auger. We get a good account here, but it doesn't match so well here. But this is then roughly the coating thickness. But the fit is not so good. If we change the structure to this structure here, we get a much better account for both the plasmon here and the background out here. So what this shows is that we have two coating thicknesses, part of the surface with 1.5 nanometers and part of it with 11 nanometers. And what this means is that we don't have an ideal coating of the PTFE. The core is off center, and since we're looking at nanoparticles of all orientations, some of them will be oriented like this, and here we'll see the small thickness, and some of them will be oriented like that, and here we see the larger thickness. So this is the determined structure of the nanoparticle, coated nanoparticle. If we look at the polystyrene, it's a little bit different. Here we find a coating thickness of 2.5 nanometer. So that would again be sort of the average coating thickness, because again the fit is not good here, although it's quite good in the background. If we change from this structure to that structure, we get a much better fit to the spectrum. So this is the structure we find, and when we interpret that, again, it's like this. Part of the surface is uncovered, so that means that the core is sticking out. It's not covered by the coating. And again, we'll be looking at the different directions. So this is what it looks like, the individual nanoparticle, coated nanoparticle, and with different orientations. We will have part of them will be looking like this, and part of them where they'll be rotated 180 degrees, and we'll see the larger thickness here. In the next video, I'll go through the details of the analysis of these coated nanoparticles.